Hello everyone. In this video, I will show how to analyze the circuits with more than one diode. In previous videos, I explained different methods of analysis of simple diode circuits consisting of one diode. But how can we analyze a circuit when there are more than one diode? We can use a diode model to analyze the circuit, but the models are different when the diodes are in forward or in reverse bias. To use the diode model correctly, you need to know which diodes are in forward and which are in reverse. For non-diode applications, it is usually easy to find out. But how can we find out in general when we are not familiar with the application? For example, if we want to calculate the current in all diodes in this circuit does not have a known application. It is cleverly designed by someone who is not known to me, just for students to practice diode circuits. Before starting analysis, let me explain the drawing for those who are not familiar with this type of drawing. When a voltage is shown at a terminal using these circles, it means there is a voltage source between this point and a reference point which is called ground. For example, 15 volts here means there is a battery between this point and ground. This is the sign for ground, and this is a battery of 15 volts. Minus 2 volts means there is a battery between this point and ground, but it's negative. It means that the negative side of the battery is connected to this point, and the positive is connected to ground. The same for minus 15 volts. Minus means that the negative sign is connected to this point, and the positive sign is connected to ground. Zero volt, it means that there is no potential difference between this point and ground. So it's directly. In electronic circuits, most of the time we avoid drawing these lines, which make the drawing too crowded. We don't have to, but it makes much easier if we could guess which diodes are in forward and which are in reverse. For example, this terminal is connected to 15 volts, and this one is connected to minus 15 volts. And the other voltages are less than 15 volts. Therefore, the voltage at point A is something between minus 15 volts and 15 volts. It should be much less than 15 volts. Therefore, D1 is in forward bias, and it is much larger than minus 15 volts. And D2 is in forward bias as well. We are not very certain about the situation of D3 and D4. It is very likely that the voltage at point A is positive from the values of the resistors. Resistors R1 and R2. Therefore, D4 is in forward and D3 is in reverse bias, because this point has 0 volts. If we have a positive voltage here, D4 will be in forward bias, and because the cathode of this diode is connected to minus 2 volts, a negative voltage, if the voltage at point A is positive, this diode D3 will be in reverse bias. But don't worry, have any guess that you like. You can easily find out if your initial guess was right or not. Let's use this guess to see what we get. To solve this problem, I will use the constant voltage model and replace the diode with a constant voltage of 0.6 volts or 0.7 volts when they are in forward and open circuit when they are in reverse. I redraw the circuit when I put the equivalent circuit or model for each diode. So I assume that D1 is in forward bias, and therefore I put a voltage of 0.6 instead of diode. And we have resistor R1. I assume that D3 is in reverse bias, and therefore I have shown this as open circuit. The same with the others. I did not draw the minus 2 volts and R3 because the diode D3 is in reverse bias, and I have shown this as open circuit. Therefore, this part of the circuit doesn't have any effect on the circuit behavior, and therefore I can remove this part. Now it is a simple linear circuit, and you can use any circuit analysis method to find the solutions. I use KVL and KCL equations, Kirchhoff voltage law and Kirchhoff current law. If I start from the 15 volts supply, I can write an equation for this loop from 15 volts to ground that I haven't shown here. So I can write 15 equals to this voltage, which is 0.6 volt, plus the voltage across this resistor, which equals to the value of resistor times the current. Resistor is 1 kilo ohm times I1. And then we will reach to point A that we don't know its value. I write it as VA. Another equation from this point to minus 15 volts. Here we have the voltage of VA, which is equal to 0.6. Let me delete this V to prevent confusion. Plus the voltage across this resistor, which is the value of the resistor, is 2 kilo ohm times I2, plus this voltage, which is minus 15 volts. The third equation from point A to 0 volts. Again, I can write VA equal to 0.6 volts plus the voltage across this resistor. The value of the resistor is 500 ohms or 0.5 kilo ohms times I4 plus 0. I can also write a KCL at point A. Current I1 enters point A and two currents I2 and I4 exit from this point. Therefore, I1 should be equal to the sum of I2 and I4. You have noticed that I have used the unit of kilo ohm for resistors in writing the equations. So the answers for currents will be in milliamps. This is a common practice in analysis of electronic circuits because most of the time the currents are in range of milliamp or microamp. If you are not comfortable with that, you can write the values of resistors in ohms. For example, instead of 1, you can write 1000 and 2500, and the current values you calculate will be in amperes. We have a set of 4 simultaneous equations, and we can calculate the 3 currents and the voltage VA. You can use any method to solve this set of equations. I found it easier to use the substitution method. So I substitute the current in the KCL equations with the value that we find from the KVL equations. So the current I1 from this equation is 15 minus 0.6 minus VA divided by 1. I2 equals to VA minus 0.6 minus 15 divided by 2, and I4 equals to VA minus 0.6 divided by 0.5. If I put these values in this equation, I will have 15 minus 0.6 minus VA equal to VA minus 0.6 minus plus 15 divided by 2 plus VA minus 0.6 divided by 0.5. From these equations, we can find the value of VA equal to 2.4 volts, and using this in the equations for the currents, I can find I1 equal to 12 milliamps, I2 equal to 8.4 milliamps, and I4 equal to 3.6 milliamp. I was right that diode D3 was in reverse bias because its cathode is connected to point A that has a voltage of 2.4 volts, and its anode is connected to minus 2 volts. Diode D3 was here. Its anode is connected to minus 2 volts, which is more negative. Therefore, this is in reverse bias. What if my initial guess was wrong? This circuit is the same as the previous one, but I have swapped the values of resistors R1 and R2. Before R1 was 1 kilo ohm and R2 was 2 kilo ohm, I have swapped the values. Let's use the same guess and solve the equations. The initial guess is that D1 and D2 and D4 are in forward and D3 is in reverse. If we use this initial guess and these new values, we will find VA equal to minus 1.7 volts. And using these values, value of VA using the KVL equations, we can find I1 equal to 8.1 milliamp, I2 equal to 12.7 milliamps, and I4 equal to minus 4.6 milliamp. Hang on a minute. I4 is negative. It means that the current is in the opposite direction of what is shown here. It goes from cathode to anode. Is it possible? Absolutely not. Current from cathode to anode is in reverse direction of the diode. And we know that the diode in reverse direction has a negligible current, nearly zero. So this answer is wrong. The analysis is wrong because my initial guess was wrong. We need to start over with a different guess. What about my guess about D3? I assume that it is in a reverse bias. The voltage at point A I calculated equal to minus 1.7 volts, and the voltage at the anode is minus 2 volts. So it seems my guess was right, but we cannot be too sure about it. The voltage of minus 1.7 volts that I have calculated for VA is based on a wrong guess. And therefore, if we calculate again and we find the right value for VA, maybe D3 is not in reverse bias. Everything will change. As a second guess, I assume that D1 and D2 are in forward bias and D3 and D4 are in reverse. So they are open circuit and the bottom of the drawing has no effect on the circuit, so I can remove the bottom of the drawing. If we calculate the current in this simple circuit, we will find that I1 equals to I2 equal to 9.6 milliamps, which is in agreement with our assumption. The voltage at point A, VA, is found equal to minus 4.8 volts. Was my guess about D3 and D4 correct? Minus 4.8 volts is less than zero. So my guess about D4 is correct because the anode of D4 has a negative voltage and its cathode is connected to 0 volt. Therefore, this is in reverse bias. What about D3? The anode is connected to minus 2 volts and its cathode is connected to minus 4.8, which is more negative than minus 2 volts. Therefore, this diode is in forward bias. My guess about D3 was wrong. What should we do now? We need to start again with a new guess. We found that D3 is not in reverse. Okay, I put its model for forward bias. I keep D4 in reverse as before. If we solve this circuit, we find that the voltage at point A is minus 2.9 volts, which is less than minus 2 volts. Therefore, my guess about D3 is correct. If I calculate the currents, all currents are positive and are in agreement with the direction shown in this diagram. As you saw, to analyze this circuit, I had to have 3 guesses to finally find the correct answer. Is it really that difficult? Luckily, no. Most of the time, we analyze diode circuits that have an application, and we know how the diodes behave. I made 2 wrong guesses to demonstrate how we can find out that our guesses were not right. Otherwise, I knew from the beginning what the current guess was, not because I had analyzed the circuit before, no, just by looking at the circuit and the values of voltages and values of resistors. For example, in this circuit, point A is connected to minus 15 volts by a resistor with value of 1 kilo ohm and is connected to plus 15 volts with a resistor with value of 2 kilo ohms. Therefore, point A has a voltage closer to minus 15 volts because there is less drop across this resistor than this resistor. So my initial guess that D4 is in reverse bias is correct because here we have a negative voltage and at the cathode we have 0 volts. Therefore, anode has more negative voltage than cathode and so it is in reverse. So I could have used this guess from the beginning and have found the answers by the first guess. Even if the circuit does not have a known application, most of the time we can have a current guess at the first time. And this is a circuit for you to practice. It is the same circuit, but I have changed the value of resistor R1. Try to see if you can find the solution with the first guess. Thank you for watching.